Hello everyone, my name is Akash Patel and welcome to my presentation on Assemble Learning and Automatic Model Tuning. This presentation is a part of the AWS Certified Machine Learning Associated course. Machine learning has become one of the most important technology in today's world. It is used in many areas such as online shopping, healthcare, banking, fraud detection, and recommendation system. However, building a machine learning model is only the first step. Developers always try to improve their models so they can make more accurate and reliable predictions. So in this presentation, we will learn two important techniques that help improve machine learning models. The first is ensemble learning, which combines multiple models to produce better predictions. The second is automatic model tuning, where AWS SageMaker automatically finds the best settings for training a machine learning model. So by the end of this presentation, you will understand how those techniques improve model performance and why they are widely used in real-world machine learning applications. So let's begin. So before learning about ensemble learning and automatic model tuning, let's first understand why improving machine learning model is so important. When developers build a machine learning model, their goal is not simply to train it. The real goal is to create a model that performs well even when it receives new data that it has never seen before. Sometimes model performs very well during training but start making mistakes when it is used in real world situations. This happens because no single model can perfectly learn every pattern that exists in the database. Different applications also require different levels of predictions accuracy. For example, if a movie recommendation system suggests the wrong movie, it is usually not a serious problem. However, imagine a fraud detection system used by a bank and uh, or a machine learning model that helps doctor diagnosis diseases. In these situations, even a small predictions error could have serious consequences. Because of this, developers always look for ways to improve both the accuracy and reliability of machine learning models. Instead of collecting completely new data every time they want better performance, machine learning engineers use different techniques to improve the models they already have. Two of the most effective techniques are ensemble learning and automatic model tuning. Ensemble learning improves predictions by combining the knowledge of multiple machine learning models, while automatic model tuning helps developer automatically find the best hyperparameters settings for training. AWS SageMaker provide built-in tools that make these optimization techniques much faster and easier to use. Throughout the rest of this presentation, we will explore each of these concepts step by step. So, ensemble learning is a machine learning approach where multiple models work together to produce one final predictions instead of depending on only a single model. The basic idea is quite simple. Every machine learning model has its own strengths and weaknesses. One model may perform well for certain types of data, while another model performs better in different situations. Instead of trusting only one model, enable ensemble learning combines the predictions from several trained models. For classification problems, the final predictions is often selected using majority voting, where the answer chosen by the most model become the final result. For regressions problem, the predictions are usually combined by calculating their average. One of the best known examples of assemble learning is a random forest algorithm. Instead of using just one decision tree, random forest build many decision trees independently. Each tree makes its own predictions and then all predictions are combined to produce one final answer. Because multiple models work together, assembled learning usually improves predictions accuracy, reduce the chance of overfitting, and create models that performs more consistently when they receive new and unused unseen data. A simple way to understand this concept is to imagine asking several experienced doctors to diagnose the same patient. Each doctor has different knowledge on and an experience. If all of them discuss the case together, before making a final decision, that decision is often more reliable than depending on only one doctor's opinion. Machine learning works in a similar way. Instead of depending on one model, several models work together to make a stronger and more reliable predictions. One of the most popular machine learning technique is called bagging, which stand for bootstrap aggregating. Uh, Bagging improve predictions accuracy by training multiple machine learning models independently and then combining all of their predictions. The process starts by creating several new training datasets from one original dataset. These new datasets are created using a method called random sampling with replacement. This simply means that some data records may appear more than once in the same dataset, while other records may not appear at all. Each newly created dataset is there used to train a separate machine learning model. Since every model works independently, all of them can be trained at the same time. This makes bagging very efficient because parallel processing reduces the overall training time. After all, the model finish training, each one makes its own predictions for the same input. Instead of choosing only one predictions, bagging combines all the predictions. For classification problem, it usually use majority voting, while for regression problems, it calculate the average predictions. Because the final decision comes from multiple model instead of only one, bagging reduce overfitting and produce predictions that are generally more stable and reliable. One of the best real-world example of bagging is the random forest algorithm. As I mentioned on the previous slide, random forest trains many independent decision trees. Each tree makes its own predictions, and then all predictions are combined to produce a final result that is usually much more accurate than the predictions from the single decision tree. This is why bagging has become one of the most widely used ensemble learning techniques in the machine learning today. So now let's move to another important ensemble learning techniques called boosting. Another both bagging and boosting combine multiple machine learning models. They work in a very different way. In bagging, all the models are trained independently, but in boosting, models are trained one after another in a sequence. After the beginning of the training process, every data point is treated equally. After the first model is trained, the algorithm checks which predictions were incorrect. Instead of ignoring those mistakes, it gives more attention to the data that was predicted incorrectly. The next model is the trained with a stronger focus on those difficult examples. This process continues as each new models learn from the mistakes made by the previous model. Because every model keeps correcting earlier early errors, the overall predictions gradually become more accurate. Since every model depends on the previous one, boosting cannot train all models at the same time like bagging. The training must happen in sequence, although these usually take more time. It often produces higher predictions accuracy, especially the complex machine learning problem. Boosting is commonly used in applications such as fraud detection, customer risk analysis, and recommendation systems, where making accuracy predictions is extremely important. One of the most popular boosting algorithm is XGBoost. It is widely used because it delivers excellent predictions accuracy while handling large dataset efficiently. Now that we have learned both techniques, let's compare them. Both bagging and boosting belong to Ensemble learning because they improve predictions performance by combining multiple machine learning models. However, the way they create those models is different. In bagging, each model is trained independently using a different randomly generated training dataset. Since the models do not depend on each other, they can all be trained simultaneously. This makes bagging faster and well suited for parallel processing. Boosting takes a different approach. Instead of training models independently, it trains them one after another. Each new model studies the mistakes made by the previous models and tries to improve those predictions. Because of this sequential learning process, boosting usually achieve higher predictions accuracy. However, it also requires more training time than bagging. Another important difference is their main objective. Bagging is mainly used to reduce overfitting and improve model stability. Boosting is mainly used when achieving the highest possible predictions accuracy is the top priority. Your presentation also highlights two well-known examples. Random forest is a popular bagging algorithm while XGBoost is one of the best known boosting algorithms. Both techniques are valuable and the right choice depend on the machine learning problems you are trying to solve. So now let's look at the automatic model tuning. When training a machine learning model, developers must choose many hyperparameters value before the training process begins. Selecting the best combination is not always easy because even small changes can significantly affect the final performance of the model. Traditionally, machine learning engineers tested different hyperparameters values manually. This meant training the same model many times with different settings and then comparing all the results. As the number of hyperparameters increase, this process become very time consuming and expensive. AWS SageMaker simplified these challenges through automatic model tuning. Instead of manually testing every possible combination, SageMaker automatically search for better hyperparameter values. The user only need to specify three things. First, which hyperparameters should be tuned. Second, the range of values the SageMaker should explore. And third, the evaluation metrics that will be used to measure model performance. After receiving these settings, SageMaker launches multiple training jobs using different hyperparameter combinations. It's compared the result from all of those training jobs and automatically identifies the model that performs the best. An important advantage is that SageMaker learns from previous training results while searching. Instead of testing every possible combination, it intelligently focus on the combinations that are more likely to improve performance. This saves both time and computing resources while working developers build helping developers build higher quality machine learning models. So to better understand automatic model tuning, we first need to understand what parameters are. So hyperparameters are configuration settings that are chosen before model training begins. These settings control how a machine learning algorithms learn from the training data. Some common examples include the learning rate, batch size, maximum tree depth, and number of training epochs. Different machine learning algorithms require different hyperparameters depending on how they work. Finding the best combination is often challenging because there is no single set of value that works well for best every dataset. A combination that performs very well for one problem may perform poorly for another. As more hyperparameters are added, the number of possible combinations grows very quickly. Testing every combination manually become almost impossible because every test requires training and evaluating the model again. This is where hyperparameters tuning become important. Its goal is to systematically search for the combination that produce the best model performance. A well-tuned model usually provide high predictions accuracy, better generalization, and more reliable predictions on new data. AWS SageMaker makes this process much easier by automating most of the experimentation, allowing machine learning engineers to spend less time on manual testing and more time building effective machine learning solutions. So, now let's discuss some best practice for using automatic model tuning effectively. Although automatic model tuning can significantly improve model performance. It works best when the tuning process is planned carefully. The first step is define a clear objective. Before starting the tuning job, we should know exactly what we want to improve, such as increasing predictions accuracy or reducing predictions error. Another important practice is selecting only the hyperparameters that have biggest impact on model performance. It is usually not necessary to tune every hyperparameters by focus only on the most important one. We reduce unnecessary training job and save both time and computing resources. Choosing the right search range is also very important. If the range is too small, SageMaker may miss better solutions. On the other hand, if range is too large, it may spend time testing combinations that are unlikely to improve the model. The evaluation metric should also match the machine learning problem. For example, a classification model may use accuracy or F1 score, while a regression model may use mean square error or root mean square error. Finally, training jobs should always be monitored to make sure computing resources are being used efficiently. Following this best practice helps SageMaker find better model faster while reducing both training time and overall cost. So, next two features that improve automatic model tuning, early stopping and warm start. So, let's begin with the early stopping. So during hyperparameter tuning, SageMaker may launch many different training jobs. After a short period of training, it often becomes clear that some models are performing much worse than others. Instead of allowing those poor performance models to continue training uh, until completion, early stopping automatically stop them. This saves both time and computing resource because unnecessary training jobs are ended early. As a result, SageMaker can focus more resources on the model that have better chance of producing good result. The second feature is form start. Normally, when a new tuning job begins, the optimization process starts from the beginning. With warm start, SageMaker can reuse information collected from previous tuning jobs. Instead of repeating the same search process, it learned from earlier experiments and used that knowledge to search for better hyperparameters value more quickly. Because of this, fewer additional training jobs are needed, making the optimization process faster and more efficient. Together, early stopping and warm start help reduce training time, lower AWS costs, and improve the overall efficiency of machine learning model development. So now let's look at several approaches that can be used to search for the best hyperparameter value. Each approach explore search space differently, and the best choice depend on the machine learning problems, available computing resources, and amount of training time. The first approach is grid search. Grid search evaluate every possible combination within a predefined range of hyperparameter value. Although this method is very uh, rough, it become expensive as the number of hyperparameter increases. The second approach is random search. Of testing every possible combination, it randomly select different combinations. Surprisingly, random search often produces results that very similar to grid search while requiring much less computation time. The third approach is Bayesian optimization. Rather than selecting combination randomly, Bayesian optimization learn from the previous training results. It predicts which hyperparameters value are most likely to improve model performance and focus on those areas first. The final approach shown in this presentation is Hyperbrand. Hyperbrand improves efficiency by quickly identify poor performing training job. Those jobs are stopped early and available computing resources are predicted toward model that shows greater potential. AWS SageMaker support this optimization technique to help user balance predictions accuracy, training time, and computational cost while building high performance machine learning model. So before we finish, let's review the main point of from today's presentation. We learned that Ensemble learning improve machine learning performance by combining multiple models instead of depending on only one. Bagging training models independently to reduce overfitting and improve stability. Boosting trains models sequentially uh, so that each model learns from previous mistakes, helping improve predictions accuracy. Instead of manually testing many different combinations, AWS SageMaker use automatic model tuning to search for better hyperparameters automatically. So understand this concept is an important step toward building machine learning models that are accurate, scalable, and ready for real-world applications. So this brings us to the end of my presentation. Today we explore how Ensemble learning models improve predictions performance through bagging and boosting and how Amazon SageMaker automatic model tuning helps developers find the best hyperparameter value efficiently. I hope this presentation helped you better understand these important AWS machine learning concepts and how they are used in real world application. So thank you very much for taking the time to watch my presentation. I would like to express my sincere gratitude to my professor Dr. Vikti Swami for his continuous guidance, encouragement, and support throughout this learning journey. His teaching has strengthened my understanding of AWS service and machine learning concept and has inspired me to continue improving my technical skills. Thank you once again for your time and support. Have a wonderful day and please like, share, and subscribe for my more AWS machine learning content.